Yeah, so I'm going to give an overview. Better? Okay, cool. An overview of field-aligned modeling. So that's 1D modeling of flares. And I'll talk about why we're doing this in 1D, not 3D, in a minute. But I want to give you an overview of the current kind of state of the field, the kind of three main codes that are being used, but then give you two examples of using these to kind of probe flare observations, and then to use observations to probe the models to show how we can work with. These have to be data-driven models. We can't just kind of model something and assume that it is a ground truth. I will say I've overloaded these slides, so there's a ton of slides here and a ton of material in them, but I will be skipping through a bunch. But if anyone wants a copy of them, I try to make them semi-comprehensive so you can go off and read them by yourself. So feel free to ask for a copy. And also, as Paul was saying, I kind of grew up in the Glasgow University seminar style with Hugh and Lindsay shouting out the whole time. So if anyone wants to interrupt or to clarify a point, then feel free. Don't have to wait to the end. So yeah. So especially the DCUS folks will know that we now have an increasingly high-quality data set of high spatial, temporal, spectral resolution data coming from both space and ground-based observations. This, including of flares. But with the increasing quality data comes the need to have equally state-of-the-art models. And that's for two reasons. One, we want to, some of this data is very complex, especially optically thick data from the chromosphere and below. So we need to forward model this data and use models to really try and extract what that data is telling you about whatever physical properties happening on the sun. But also, the observations are the ground truth. And so we have to see if our models are consistent with the data in order to work out, is this physical theory we have correct, or are we doing something wrong with the models? And so I'm going to talk about field-aligned models. These are 1D models aligned with a magnetic field of flares. And we use 1D models because in order to get the really high spatial and temporal resolution needed for flares, we need to have study the detailed microphysics of radiation transfer involved at very, very fine scales that are not currently computationally tractable in 3D. But I'm going to show you at the end, flares are a 3D phenomenon, and so we have to kind of think about when we're looking at the output of these codes, how do we interpret those, and how can we do some clever analysis to actually kind of get at 3D effects, even using the 1D models. And so yeah. And I also couldn't give a talk at near NSO and talking about high quality data without showing this the recently released movie from DCUS. And I was saying to Adam and Janet earlier, I'm getting a little bit scared looking at this for the prospect of flare observations, because I think they're going to be such high resolution that we're going to realize that the modeling challenges we have are even greater. But I am quite excited to see the equivalent with a flare right in the middle for here. And so for those of you who are not super familiar with flares, I'm going to describe the standard flare model. And as I go through the talk, you'll see that I'm going to point out some things, some evidence that we may be missing ingredients from this model. And so this is, again, it wouldn't be a flare talk without the gratuitous 1D cartoon of a flare. And so flares are transient energy release events, and we think happening in the corona that release stored magnetic energy, vast amounts of this, up to 10 to 32 ergs in large flares. That's liberated through magnetic reconnection and transported down magnetic field lines to the denser transition region in chromosphere, where this energy is dissipated and heats the plasma, resulting in broadband enhancement to the radiative output from the sun from different types of sources. We have ribbon sources, or these extended sources in ultraviolet and optical, and then we have these compact foot-point sources in hard X-rays and some other sources. And because we see hard X-rays, that's kind of unambiguous evidence that there are accelerated particles during flares. And we suspect this is coming from electrons accelerated in the corona that are fired down these legs, impact the chromosphere, and release their energy through Coulomb collisions. And we usually talk about non-thermal electron beams. Really, protons and ions are probably accelerated as well, but we're only just starting to kind of include those in the models. So when people discuss the standard flare model, it's electrons are fired into the chromosphere, dump the energy, and everything gets hot and expands. And because it expands, you get flows produced, so you get evaporated upflows, you get dense condensations going down towards the sun. And yeah, so part of the job is then to study the chromosphere, because the chromosphere is the site where energy is deposited and the site of or the origin of the bulk of the radiative output. So if we want to really understand energy transport into the chromosphere, we have to kind of get a handle on all that radiation. And so yeah, just an outline of what I'm going to talk about. So I'm going to summarize the current flare loop models and show two examples. One of a lower atmospheric radiation source, so white light flare, so optical continuum enhancement. I'm going to show what the model of the standard model predicts and how that compares to observations. Then I'm also going to show the coronal response from these models to show how we can look at iris results and think about, can we create loop arcade models from these 1D flares. Oh, that slide repeated for some reason. 3 times. Okay, so these are just some sample outputs from flare models showing we get these 1D kind of temperature, electron density structures. We can produce synthetic radiation. This is kind of a preview from what I'm going to show later of these arcade models. But these models have a rich heritage from their versions of these from decades ago, and over time we've now kind of got much more state-of-the-art resources that are built on these early attempts that include full radiation hydrodynamics. So that is the coupling between the radiation produced, the energy input, and how they affect each other. And that's really what we need to study the kind of non-local thermodynamic equilibrium of the chromosphere and how that feeds back in to showing how you put energy into the system, how does that feed back into the radiation produced and vice versa. Yeah, as I said before, we really should be doing this in 3D, but to keep the problem computationally tractable, we had to do this in 1D. I think these are all points I've already made. Apart from, this is a very important point that I think people think we often ignore, that if the standard models that we run fail to reproduce observations, and I'm not saying that I need to get exactly the right intensity or line width, because you're never going to get a one-to-one match. What we want to see is consistency between the observations and the models. Then we have to kind of go back and revisit the underlying physics of these models. Yeah, I made this point already, so I'll skip over. So there are 3 main flare loop models that are kind of used by the community, each with various different states of development. You might have heard of some of these. So I think you've probably heard of Radon and Hydrad, but Flarix is another Radon-like model, so it's a radiation hydrogen model produced by some colleagues at Orange Observatory in the Czech Republic. So these are just kind of a summary of how they differ. But I'm only going to focus on a couple of bits here. One is the RHD codes. Their main selling feature is they have an accurate chromosphere. So if we want to model the energy input into the chromosphere, we want to make sure we're modeling those non-LTE processes properly. Hydrad was designed initially to look more at coronal processes, looking at nanoflares, but it's since been adapted. So they use approximations to non-LTE for hydrogen and lookup tables for radiation losses. So that's how the main reason the codes differ. Also with the geometry. So we all use some sort of adaptive grid to capture shocks that form. And then the style of the heating. So we all inject electron beams, but there are different treatments of how you solve that transport problem. So you can either have a test particle code, or you can use kind of analytic approximations, or you can do what we do with Radon, which is the code that I'm most familiar with when I use my research. You can solve the full Fokker-Planck treatment, including transport effects as the beams propagate from the corona down to the chromosphere. All the codes include conduction, and these codes have also got an approximated form of alpha-ionic waves that I'm not going to discuss here, but I think this is kind of an exciting recent development that we're starting to include, because it's clear that was clear to me, and hopefully I'll point this out, that we're missing some ingredients in these models, and I think this may be one. And yeah, these are just the code papers as they are. And so one question that seems obvious, but hasn't really been done, is how do these codes compare to each other? And the answer is, well, we're starting to do that now. And that's because there are different states of development. They've been used for different purposes over the years. But also, this is not exactly, it's not easy to get funding for this sort of code purpose. Because we want to turn around and say, well, the FLIR community is starting to kind of rely on these codes to kind of guide the research. Are we doing a good job? Are we all at least doing the same wrong thing? Or are we all doing everything wrong? Or everything right? So this is just a kind of advert for the fact that we are doing this now. But also, these are the first attempts to do this. And it shows that, so this is radon and flare, its comparisons at different times. This is 3 different times in a flare. And you can see the black and red lines overlay each other remarkably well. So these codes have different numerical setups. They have some different physics involved. But if we kind of optimize the problem so they're all using similar physics, then we get remarkably similar answers. Even these small features are reproduced, which gives us confidence that we're at least along the right track. This is a radon and hydride comparison. That's clearly not as good. So the black line is radon, the colored lines are hydride. And they are multi-fluid codes. So you've got electron and ion temperature. You can see that there's a big disagreement here in the temperatures. But I should point out, this is not optimized. So these were just kind of 2 codes with similar inputs, but we didn't optimize the problem to just investigate the numerics. But even from our initial looking at test, we think this is because of lack of radiation transfer in hydride. We think this is the lack of helium is causing this bubble. So it kind of points out the fact that we can learn from each other. So you can see that hydride predicts that ion and electron temperatures are very different, which radon does not include, but the helium has a big impact. And so now the job is to take a step back and work out, okay, how do we steal bits from each code to make a kind of optimal problem? Yes?
The temperature plateaued about 20,000 degrees in the pre-flare.
Yeah.
It'd be like force fell 3 seconds.
Yes. Yeah. So this is that's a good point. So typically we don't in radon we use a radiative equilibrium atmosphere. So it's kind of not really got a hot chromosphere. But for this problem, we wanted to match the flare-X initial condition. So we just forced a val C and had a heating function to maintain that.
Cool, thanks.
Yeah. So in conclusion for the state of the codes is that we are now all working together to try to work out, are we doing things correctly? So I'm going to leave that bit aside and focus on using the radon code to look at white light flares. And so white light flares are enhancements to the optical continuum emission, and these represent a large fraction of flare energy. So it takes a lot of energy to produce a noticeable enhancement over the photosphere during a flare. And we can see contrasts ranging from a few percent up to a few tens of percent. And in some flares, very small sources show hundreds of percent enhancement in the optical continuum. And partly because of the difficulty in observing these, they were being perceived as big flare syndrome. So these only happen in big flares. But we now have evidence that they're actually appearing even in C-class events. And in a study by Kyoko Watanabe of M and X-class flares observed using Hinode SOT and SDO HMI, roughly half of these were white light flares. And so white light flares seem to be a fairly ubiquitous feature, or the optical continuum enhancements are a fairly ubiquitous feature of these flares. And they seem to represent a large fraction of flare energy, but we don't really know what's producing them. There's a large ambiguity in where they're produced in the sun's atmosphere, what mechanisms produce it, how energy from the corona reaches the required location to heat these flares, to produce this white light. And because of this, white light flares place severe constraints on energy transport mechanisms. And so it's one of these things that I like to turn to when we're testing energy transport mechanisms is, can we reproduce white light observations? And so this is a very simplistic overview of the two competing ideas of white light flares. Probably it's a mixture of mechanisms, but these are kind of the two camps, as it were. So one is you've got a photospheric origin, where you increase the temperature of the photosphere by a few hundred Kelvin, producing an optically thick source. It would be black body-like. But the problem here is electron beams can't reach the photosphere electron beams as we currently model them cannot reach the photosphere or interpret the data from RESI. We inject these non-thermal electron distributions with parameters that are obtained from hard X-ray observations from the RESI spacecraft. So we get a slope of the spectrum, we get a low energy cutoff and a flux, and the observations we've been seeing from RESI show that there's not enough power in the higher energy electrons that are able to penetrate deeply to power the white light flare. Radiative backwarming has been proposed as one means. So you heat the chromosphere, and then you get radiation going up and down, and that radiation going down heats the photosphere. But it's not really been shown to be able to produce the full white light flare yet. And I'll show some modeling of that in just a minute. So then there's a chromospheric origin, where the electron beam makes it to the chromosphere, it over-ionizes the region through heating and ionization. You then get a lot of hydrogen recombination, resulting in a free body spectrum that forms. So you get recombination radiation, which would become coming from an optically thin layer in the chromosphere. And this is a very observationally indicative feature of this, which is the presence of a Balmer or a Paschen jump, which has been observed with some flares, but not every white light flare. And so there's some evidence that white light sources can be fit by black bodies. And so there's evidence from both regions, but there's a paucity of observations. And so there's not enough broadband spectra to really discriminate these models. This is just an example of this feature. So you get these jumps in the spectra. So I wanted to look at what does the standard electron beam model predict from white light flares? Can we do it just with the physics we're already including, or do we need to add some more physics? So I ran a large grid of simulations ranging from very weak flares to what we consider strong flares, but are probably in reality just moderately strong flares. This is just the edge flux you're injecting. These are various spectral slopes ranging from what we call a hard beam, which means you've got a relatively larger number of high energy electrons, and so they're able to penetrate deeper, to a soft beam, so in a kind of simplistic way, you're heating deeper with these beams and heating higher in the atmosphere with these beams. So we injected these electron beams with this profile, a kind of triangular pulse. And here I'm just going to focus on these high energy simulations. There's a whole other discussion with lower energy case of black light flares and dimmings in the continuum that I thought to take place, but that's a separate talk. So we have like 13 simulations to compare. So that's just these here. So these are an overview of the temperature, electron density, the hydrogen ionization fraction, and then the beam heating rate from each of these simulations. And I've ordered these in terms of, throughout the talk, you'll see the same ordering. These are ordered from number of electrons at 100 keV. So the harder beams have more electrons at 100 keV, so they can penetrate deeper. And you can kind of see that happening here. You see that the more deeply penetrating beams increase electron density over a much larger swath of the chromosphere, whereas the soft beams only really impact the top of the atmosphere. You don't really get much of an impact lower down. So we ran these simulations, and we want to look at the emission mechanisms that produce white light observations. So working with Adam, I looked at the contribution from various sources of the the hydrogen continuum. So recombination processes to hydrogen, the H minus, which is the emission mechanism that produces the kind of black body light we see from the photosphere. We included various scattering terms of metals and free processes. And I've highlighted these because I'm going to just focus on these for the rest, as talk goes on. But we did include everything else, but these were the most dominant. And so if you sum these up and then integrate it through the height, you get the emergent intensity. So we can compare both the emergent intensity and each of the emissivities as a function of height to work out where in the atmosphere are these white light flares originating. And that is here. So this is an example of for one simulation at the peak of the flare, or the peak of the energy injection at least. And the blue line shows a pre-Balmer jump wavelength, and the orange shows a post-Balmer jump wavelength. This is the optical depth. So the dotted lines are the pre-flare. And you can see that while the opacity increases during the flare quite substantially, where the flare is forming, so this is a function of height, where the flare is forming here, it's still an optically thin plasma that's being produced. So both the pre and post Balmer jump emission, so the Balmer and the Paschen, is optically thin, coming from the mid to upper chromosphere. And I noticed that there's a fairly consistent temperature range here. Throughout all the simulations, the white light was coming from an 8 to 15,000 Kelvin plasma with, in this case, an electron density of 10 to 12 or 13. And I'll show that the electron density is really what kind of guides the intensity of the emission in these cases. And there was some contribution from H minus opacity, but it was optically thin H minus opacity, so it's kind of, you're increasing the temperature on the way to the photosphere, producing some H minus, but not enough to make it optically thick. And this is just an overview of all the simulations to show that even in the most deeply penetrating cases, we get optically thin emission from the chromosphere. But you can see that as I showed with electron density, the width of this emitting layer is really dependent on the beam parameters in this case. So the more deeply penetrating beams, so these harder beams, involve a much larger swath of the chromosphere. And actually, in these cases, so these kind of red and orange cases, H minus emission was actually responsible for between like 40 and 50% of the emission at certain stages in the flare. So while it's optically thin and is dominated by recombination, we can't just ignore this other emission source. As an aside, it's a very tricky observation to make, but models like this kind of indicate that if we had a limit observation, you should see varying source sizes for continuum emission, depending on the beam parameters. But it's only a few hundred kilometers thick, so you have to have a very, very high resolution instrument to see this. But I think there have been observations of varying widths as a function of the beam parameters using HMI and RESI, but I think it's kind of on the borderline of being detectable or not. So yes, I mentioned that there are a couple of mechanisms here. So I want to show how dominant is recombination. And this is a log scale. So you see that it is the most dominant, even though the H minuses have an impact. But this changes pre and post Balmer jump. So this is before the Balmer jump, where there's very little H minus emission. But after the Balmer jump, for this hard beam, this deeply penetrating beam, it's roughly 50-50. Which means that we're getting contributions from not just one layer, as we are, or one mechanism as we are from here. But this changes with beam parameters. This is the more typical beam, which is delta phi, kind of mid-range spectral slope. And we can see that the H minus opacity doesn't increase that much during the flare. It's dominated by this spike of recombination radiation. And so the point I was making at the start of the talk is that we can do all this analysis and we can look at where the model predicts this emission comes from, but we have to take a step back and say, well, is this consistent with the observations? And in this case, we're kind of mostly there, but not quite. And so these spectra are the synthetic spectra from the models. And I've overlaid 5 different flares that were observed. There's I didn't realize until I did this, there were very little calibrated white light data available in the literature. And by calibrated, I mean it's not just reported in dNs per second with light curves. We have the physical units of ergs per whatever your choice is. So I didn't really have much to go from here. So these are from various sources. The more recent ones are from HMI and SOT. There are some here from, I can't remember, ground-based data as well. And I've highlighted this strip here. This is where HMI is. We have to be very cautious of HMI data during flares. And we're not entirely sure if we can trust that photometry, because they're fitting this line, and then during the flare, the line is going to go crazy, and they don't really account for that in their pipeline. And so Mikhail Svanda and some collaborators did an investigation of this using the raw data, and showed that actually, yes, you do have to take during flares, and I think also planetary sunspots, you have to take the HMI photometry with a grain of salt. But you can see here that these data points, so also these data points in here, are a range. So there's a range of SOT data. But you can see that by and large, the intensities match. These are all flare excess. So you see the intensities are consistent with our modeling. We didn't set out to model any specific flare with any specific pattern. And so we're not expecting these all to line up on one of these curves. But the fact that they're all kind of in this ballpark is encouraging. We don't have observations up here, for example, out with the range. A point to note here is that all of our synthetic results have a Balmer jump. We weren't able, using the standard model from flares, to produce any sources that did not have a Balmer jump. And we're not able to produce any solely optically thick white light flares.
Can you tell us the data source again? It's the shortest wavelength is iris.
Oh yeah, there's also this iris point here. Yeah, this is I'll comment on this again in a minute. But iris observes the near ultraviolet in several kind of quasi-continua passbands. During flares, you got a bunch of lines forming, but you can grab narrower regions of continua in between these lines and grab what the continuum should be there. The rest are all either HMI, SOT, or ground-based.
And then accounting for the different spatial resolutions.
Oh yeah, so we haven't done that at all. This is why I'm saying this is just a kind of a first pass. If we take the reported flare excess, are we consistent? So you're right to point out that the space-based and ground-based data are all going to have different temporal resolutions, different spectral resolutions. A lot of these are images, and so it's not just one, they've been kind of averaged over some image, and SOT has a couple of angstrom passbands, so you can probably get a couple of lines in there as well. So this is just showing some other data. This is work from Peter Heinzel, showing cuts through the HMI compared to, these are RESI contours showing the hard X-rays to show that the white light and the hard X-rays are very spatially and temporally correlated, which is an indication that they're caused by the same source. You get electron beams coming in, you produce X-rays, white light is produced in the same spatial location, or roughly the same spatial location. So that's part of the evidence that people think these are chromospheric events. But you can also see the heights of formation. If I go back to here, in our models, the heights we're getting are mid to upper chromosphere, so roughly 800 or 700 to 1100 kilometers. This is very consistent with observations that Peter made, showing that you get roughly 1,000 kilometers, give or take. These are 3 different flare observations showing the presence of a Balmer jump, presence of a smeared out Balmer jump, and a lack of a Balmer jump. And these are showing you can get different results from different flares. I think Adam has done some work to explain why this is smeared out.
Is that just a matter of the input energy?
I don't think so. I don't think we've got a good handle on why some do not have Balmer jumps yet. I'll show a couple of slides the on the next slide, some SOT and IRIS observations that kind of back up the fact that some sources do have and some do not. I think it's probably a sign that we're not heating the lower atmosphere in the models sufficiently. So that could be the beam parameters and the fluxes, but I don't think we can get heating to those levels just with electron beams. I think we have to think about proton beams or other sources of energy transport to really get that. But I think it is a sign that we're heating different places. These are all kind of historical observations. Recently, we've been limited to SOT, HMI, and limited ground-based. These are all sporadic observations. We've not had good sampling of the optical continuum for many decades. And I'm hoping DKIS can help this by observing multiple pass bands using different instruments for flares. So this is some work using SOT and IRIS. So SOT gives you the optical continuum in 3 filtergrams, so a red, green, and blue continuum. These are narrowband filters that you can calibrate using distant optical data. They've also got this IRIS observation in the NUV that I commented on a moment ago. This is this kind of quasi-continua you can grab out. And there are 13 flares, I think, or around 13 flares that have joint SOT and IRIS observations that are confirmed white light flares. There could be more. These are MRX flares. There could be a bunch of SEEK flares that we haven't looked into yet. But of the large M and X-class flares, there are 13 observations that no one's dug into yet. And the reason I'm showing this here is that if we grab 2 different sources from this flare, so these are sources A and B are positions where the iris slit. So iris is a slit scanning spectrograph, for those who are not familiar with the instrument. So they slit scans across the field of view, various, I think in this case it was 4 different slit positions. This background image is SOT. The colored sources here are the different time that I detected white light emission from SOT. And these are 2 positions where the slit from iris was coincident with the SOT data. And so you see in source A, so the black data points are the calibrated data. And I just overlaid black bodies at different temperatures. I'm not trying to fit this properly. I just said if I've got a black body at this temperature, what is the curve? And you can see that, and this dotted line is a Balmer jump. You see that these data all are kind of roughly falling over a black body curve with roughly the same temperature. But the important thing is here, there's no, the NUV, so the point before the Balmer jump is way lower intensity than the optical points here. But in this other source, just a couple of arc seconds over, a few arc seconds over, there's while the optical parts are well fit by a black body, the NUV is not. This is Balmer jump presence. So there's both a Balmer jump and not Balmer jump in the same flare at roughly the same time. And so this is kind of pointing that while we're getting roughly consistent intensities, we're not getting the spectral shapes we need from the models yet. So this is pointing that in this source, something else is happening. It's not just a standard flare model of electron beams. And I've not had a chance to dig into this further yet, but I'm hoping to study these 13 flares in detail, and then go back to the models and see, well, if we add this to the model, can we get more consistent results? Oh yeah, sorry, I meant to go to this slide. It's just summarizing what I just said. So to summarize the white light portion of this, I'll leave this here to say that we're on the right tracks, but there are indications that we're not. There are missing ingredients in some flares, and I think it's a sign that we need to be heating the lower atmosphere. I'm hoping that further observations from DKIST can help support these modeling efforts. So, skipping on to the next topic I want to go into.
Hey, Graham.
Yes.
Sorry. How do you combine the optically thin recombination continuum in the hot chromosphere with this other thing that you just described. I mean, that is fairly hot. You have an 8 to 15 kilokelvin plasma, and this is much lower. It's 5,500 Kelvin. So do they both occur in the same flare? Or, I mean,
that's what we don't know. So the models are saying that you get this hot optically thin component, and that's the main contributor to the flare. These are all flare excess. So I subtracted the photospheric contribution. In the cases where, like this one, so either this means that we somehow skipped the chromosphere,
right,
and we're only heating the very lower atmosphere, or the lower atmosphere is just so much brighter. So if you heat it up sufficiently, it's an optically thick source, that even if there is an overlying chromospheric source, the dominant feature is this hotter photosphere. And so it then becomes the difficulty of, can you subtract these and get different components? And similarly here, an idea I want to explore is to say, well, okay, if we believe this is recombination, because I don't think the photosphere would produce sufficient quantities of near ultraviolet, then we can very, very loosely, because only one data point, get there. If we say, okay, well, if we assume it's a temperature of 10,000 Kelvin, that we need a density of X, can we roughly estimate the contribution from the optically thin source, subtract it, and what's left over is the photospheric source, for example. So there's a lot to play around here. The problem is the lack of data, the lack of broadband data in these. So this is the lower atmosphere, where we have some issues. We can also use these codes to look at the upper atmosphere. But when we look at the lower atmosphere, while the viewing angle and loop positions does have an impact, these are forming from what we see in the observations from a very, very narrow region. And so we don't really have to worry too much about the extent of our loop. We kind of assume it's all happening from this very thin layer. We can forget about kind of viewing angle effects, roughly. But when we're thinking about emission coming from the corona, from this flare-headed corona, like these arcade structures and these loops, we do have to worry about the shape of the loop and how, with optically thin emission, emission coming from here is being added to other different loops, and the geometry all has an impact. And so, does that mean that we can't do coronal observations with these models? And hopefully I'm going to show you the answer is no. So this is the 1D prediction for iron 21. So iron 21, 1354, is a hot coronal line that's produced during flares, observed by the IRIS spacecraft. And these are the results. Yeah, it's taken a flare, synthesizing, just using Chianti data, the iron 21. These pixels show different snapshots. This is the time function of wavelength. And this is showing the contribution function of the emissivities from different snapshots in the flare. And you can see that these lines are asymmetric. There are multiple components popping up, which is not really observed. Typically, these lines are very symmetric when they're observed. They start blue shifted, start very blue shifted, become less blue shifted over time, and they're typically they start very blue shifted, very broad, become more narrow, and as they come back towards the stationary or the rest wavelength during the flare. But here we kind of get these multiple components, and that's because when you're looking at this line from these 1D models, we're kind of assuming it's this vertical monolith. We're looking straight down, and we integrate up through the entire height, and we're integrating many, many megameters in one go, which means we're kind of pushing together features forming at different heights, and you get these shoulders forming. In reality, when we're looking at the IRIS observations or similar observations from ICE or other coronal lines, we're only looking at segments of these loops at a time, because one IRIS pixel is, 300 kilometers, 700 kilometers. So we're only really looking at part of this loop. But the next pixel is the next part of the loop. And so doing this comparison is a bit misleading. And so we wanted to think, how can we still use our models, but in a more clever way? And so we started to think about developing this loop model. And so my postdoc advisor, Joel Allred, for a completely separate bit of work, was looking at some nanoflare simulations, where he used Marcus Husbandon's extrapolation routines, got a 3D box of an magnetic field with each voxel, and he then so we had, using the AIA data and HMI, we can actually track the AIA loops from this active region. And so we went back to that active region. It didn't flare, but it had these loops. And we chose 180 of them to say, well, what if these are our flare loops? And we chose these to be roughly the right size to match our modeling. So roughly 20 megameters from one end to one end. And we then just grafted the DEM from our model onto each spatial location. So we kind of wrapped the DEM from our loop point to our foot point to loop apex on one half, and then symmetric on the other side as well. So we have these symmetrically grafted DEMs, and also VDEMs. We wanted to include the velocity information to generate the spectral lines. And we did this in a way to mimic the RK structure by activating each loop at a different time. So we started. At any one snapshot of this arcade model, we're going to have loops that were activated, loops that were peaking, loops that are in the cooling phase, to kind of mimic this whole kind of global evolution of the flare. Sorry, I should have said, we then take this 3D structure in each voxel and project it onto the 2D plane to mimic AIA or other observables. So this shows a snapshot of this. In fact, I'm going to just skip over to the next slide, show the movie. So this shows synthetic AIA movies of this flare arcade that we have not saturated. So these, in reality, would be saturated, but we took out that feature of the pipeline. The GOES light curve. So we got an M4 flare without trying. I also want to point out, this was the first attempt. We didn't set out to activate these loops in any special way, but it just kind of so happened that we were able to reproduce a nice GOES light curve the first time, and so we kind of stuck with that. But this is actually was quite surprising to us. We managed to get an M4 flare with this nice kind of rise and decay that matches GOES pretty well. And these just showed snapshots of the DEMs in various temperature bins over time. So I'll play that again. Yeah. What else I want to say about this? I think that's all. Oh yeah, so there are two maps here because we had the active region in the original location, but as I'll point out in a few slides, we got some surprising results. It's because of loop orientations. And so we thought, okay, this is a clear viewing angle effect. So we rotated the entire region 45 degrees to near disk center to show the impact of if you're observing this active region disk center or observing it at where it was along the limb, because it's quite far across the disk. And so going back to Iron 21, we used the same process that we used to get AIA. So we took our VDEMs in each voxel, projected that onto a 2D plane for each pixel, and that meant that we're getting in each pixel you could have a contribution from multiple field lines, multiple loops, and you're self-consistently taking into account the superposition of loops, geometric effects, and the viewing angles. And when we did this, we passed it through the iris response. So we added some Poisson noise, integrated over a typical iris exposure time. We used effective areas from the status changes during the mission. We should note we're actually a little bit worse than iris because we did this on an AIA map. So the pixel dimensions are 0.6 arc seconds, which is not as good as iris, but we didn't want to have to reproduce the whole projection matrix for iris. But try to get as close as possible. We added a background continuum, just using the Radon simulations, and then produced this map. This is a snapshot from one map. And so you can see we have this arcade structure various kind of pretend slit positions, and then the synthetic iris observables. And if people are familiar with iris observations of flares, these are remarkably flare-like from the observations. And I'll show a movie showing that from each region, showing that we do get these these blue shifts that go background. You can see loop-top sources are stationary. You get broader sources. Yes, these are the two different regions. And these big kind of strips that you see are the fruit points. So you get these bright continuum sources that then kind of give way. So this also shows why we can't see iron 21. So iron 21 initially is lost in the noise of the continuum. Then we see these blue shifted sources after the light gets strong enough to be observed above the continuum. So it's great. So we can use these, but then we want to, now that we have a more realistic comparison to make against the observation, we want to actually do something with this. So we want to look at some statistics of the data. I'm going to skip this slide. So we can look at Doppler shifts to see, and this is the reason that we rotated the background. And so initially, we just fit either a single or double Gaussian, if necessary, to these spectra, and we grabbed the resulting Doppler shift. And when we plotted it at various snapshots, we realized, oh, it's weird. 1/2 of the arcade structure is what? So the Doppler shifts kind of map the fruit points. The strongest Doppler shifts map the fruit points of these loops. But we've got this redshift on one side, even though the input model was all flows against gravity, which would traditionally be thought of as upflows. As we stared at this for a while and kept thinking we'd made some coding mistake, just projecting the loop somehow, but it turns out these are just very, the projection of these loops is such that they're very inclined against the surface. And so when you're looking at it on the disk or over the disk, even though the flow is against gravity, the flow is away from the observer. And so we get this redshifted structure, which we only really can pick out if you see the full thing. So if you only had one slit position and didn't really have the loop information because the AIA is saturated, you wouldn't really be able to figure this out. So this points to me to show that we need to kind of have unsaturated coronal loops during flares. So we rotate it background to the center, and everything is blue shifted as we expect. So everything was fine. I will say we do get some redshifts here because there is a sloshing back and forth. We have a boundary condition in the model where we get this reflection to mimic incoming disturbances from the other leg of the loop. So towards the end of the simulation, we do get a tiny redshifts of sloshing around. And these are just movies. Oh. These aren't movies. These are just these are movies of just the flows in each arcade model. And the background image is just the intensity showing where these red shifts and blue shifts are forming.
Surface plot.
Yeah.
Z is out.
Yes. You know, this is, if you just imagine you were looking at an AI image or an iris image, this is what you would see. So all the projections and everything are done properly.
Can you play it again?
Yeah. Maybe. Oh, it's playing. Cool.
Not at the same time.
I mean, there are some bad fits that are popping up and down.
But you don't have any serious, strong, real downflows in when you rotate the thing to the.
When we rotate to the dead center, no, we don't. So that was all a viewing angle effect on the disk. Then we can look at line width and asymmetries. And so previous modeling of iron 21 it's been difficult to get broad but symmetric profiles. And we kind of did a little bit of a better job here, but it's still not great. So I'll show the line widths here. So we do get broader profiles, especially in the altitude of the flare, that become more narrow as we go on. But again, show movies of these. Yeah. So as you get closer, as the time goes on, these become much more narrow. But if we compare these to the asymmetries, it's kind of hard to see in the scale. But we do actually measure, well, we get broad profiles, the asymmetry increases from these lines. So that's kind of indicating to us that, in fact, I'll show a movie of this as well. So you should see kind of like clusters of, getting more asymmetric. And that's a propagation of this arcade. So that's kind of indicating to us that something's missing in the model to make these broad but symmetric profiles. So all we have here is thermal broadening. We've not included any turbulence or anything kind of fancy. So showing that thermal broadening alone with superposition of loops is not enough to make a very, very symmetric profile, as is observed using IRIS.
What do you mean by turbulence?
Well, just the usual microturbulence definition that people use to have broad profiles. I don't have any. I'm not inferring any meaning of what's causing the turbulence or. So again, compared to observations, so a few years ago, Jana and Dave Graham made a very now famous plot in the flare community, showing from a sit and stare observation of a ribbon that passed through the iris slit. They observed the Doppler shift of this iron 21 line as a function of time. And they overlaid these, so I believe this was ordered from the first detection, or is it the peak? I think it's the first detection. The first time you could see the line.
No, it was actually timed to the chromospheric flows.
Oh, to the magnesium. Okay.
Magnesium 2.
Okay.
Yeah, the maximum of the redshift.
Okay. So we can see from this that the iron 21 line in this flare started off very broad, blue shifted, and over a period of a few hundred seconds, moved back to rest in a very ordered fashion. There's not much spread here in this main population. There's a second population that I'm not entirely sure we know what is caused by this.
I remember this. We cut them not from the very beginning of the event. I think you see if you shift that.
If you shift this over, you mean? Okay. But anyway, so there's not much spread, and they all very consistently return to rest, return to the kind of stationary line in a similar time scale. So if we can repeat this superposed analysis on the models and see, well, are we getting something similar? And qualitatively, we are. We're getting lines that are initially very blue shifted, move to rest, but there's a difference. Also, I'll point this feature here is because we get this sloshing around because of the boundary condition in the model. So that's just a feature of the fact that we get this kind of rebounding effect. And this is the disk center, and this is the one around the limb. So we get these red-shifted bits that are kind of confuse things. But overall, we can point out that the clustering is much larger, or it's much smaller in the observation compared to this large spread of velocities in the model. So we're not as consistent there. Also, the timescales involved here are very much reduced in the model. And this is kind of a problem I was hoping we would get rid of by moving to this kind of arcade-like structure. But we're still, the blue shifts from these are dying down within 100 seconds, which is a much faster timescale. So this is showing us that we're missing something in the modeling. We're missing some ingredients that are maintaining these blue shifts over the course of the flare. And we can similarly look at the line widths, which I believe Dave is now done but hasn't published yet. Is he not?
I don't know.
Okay.
I had another language.
Just show that we have a similar time scale. So it takes a little bit longer to reach the peak, but after the peak we have this kind of 50-second decay back towards this thermal width, or the rest width. skip this. So this is a summary that we are now able to really think about how to model these optically thin coronal emissions from these 1D models. So we can keep what I think is the accuracy of the 1D approach by having all these complicated physics with the right spatial and temporal scales, but still address the coronal portion of these model data comparisons. But these model data comparisons are showing us that we're still missing some things, and mainly the timescales. So we need to go back and think, why are we missing these? Why do we not have long duration flows? And also the fact that we get broad lines but asymmetric lines. So what are we missing to keep these lines symmetric? Is it some sort of turbulence? Do we alpha-enic waves? Is it non-equilibrium effects? So could it be that the iron 21 is actually a much hotter temperature than the assumed kind of formation temperature from equilibrium processes? And that's something we're actively investigating, because there are methods we can use to get the non-equilibrium ionization fractions, etc. Yeah, put this here. So I'm just going to throw out some conclusions and welcome any questions people have about flare modeling.
Have you experimented with different ramp downs in the heating rate?
For this arcade modeling?
Yeah.
No, not yet. This is like the first attempt that we're going to write this up as our first pass, and then delve into doing it in a bit kind of fancier ways. So right now we graphed one simulation onto every loop. In reality, each loop's going to be a little bit different. So what we want to do is go find an actual observed flare, trace those lines, and use RESI-derived parameters as a function of time to drive different simulations, which we'll be using the observed ramp up and ramp down to try this.
Question, did you assume unresolved loops?
Sorry?
Did you assume unresolved loops?
Yes, so they are resolved as much as AIA will resolve it. So we used AIA, Marcus Vanden's routines, to get these. And so we're imagining we have one bundle of loops as an AIA resolution. Although we do take into account area expansion.
Because I was going to
Yeah,
ask
so Marcus's technique does include that, yeah. Yeah, sorry.
Are there any possibilities for 3D modeling of other lines, like more chromospheric?
The chromospheric is tricky. So we're able to do this because they're optically thin, with this technique, because they're optically thin. So we can just add up the emission from where it's coming from. If you want to look at lines that form with significant opacity, then you have to really think about the scattering of those photons, how the line of sight effect. Yeah, it's a much more complicated problem, which is why we need radon and other non-LTE codes in the first place. I know that one attempt that we're going to do is just to investigate the impacts of 3D effects on line widths and stuff like that. I want to work with the Scandinavian crowd to take so they've got multi-3D, which is 3D radiation transfer code. They can deal with the effects that you need to, like PRD, for example, for these lines, and just kind of create a very ad hoc flare atmosphere to put into that model. So it'd be very, very simple. So just take a few of these radon loops and kind of have it decayed out of the quiet sun and put it into their box and see what happens. Which wouldn't be simulating a flare, but it'd be looking at, okay, if we have this really hot chromosphere, what effect does 3D have? But this approach is not possible with 3D yet. Oh, sorry, with optically thick lines yet.
So, I appreciate the careful study, and that it's not my field. I appreciate this is not easy, but the inability to reproduce the Graham and Kautzy observations of the behavior of the iron 21 looks like this isn't just throwing in microturbulence or some alphanic waves. It looks like you're missing an ordering principle.
Yes. So I have my own thoughts on what's causing this and some approaches to address it. So this is, for the white light stuff, this is using the standard model electron beams, which I think is becoming more and more clear that the way we're modeling these is not sufficient to reproduce these observables. And so there are some things that will help, I think, increase the timescale. So right now, these models cool very, very quickly. The second you turn off energy input, so the minute the beam ceases injecting energy, the atmosphere cools very fast, which means the flow is stopped and everything else kind of shuts down. And so I think that the thermal conduction, the way that's treated in these models, is a main factor here. And so we are looking at incorporating non-local effects and some turbulent suppression of conduction into the models following some work by Gordon Emsley and Nick Vian that I think will increase the lifetime. So they did some work using some much simpler codes, so using EBTEL, which is a 0D kernel code, and they found that if you suppress conduction, you can increase the decay times by orders of magnitude. And just kind of some initial experimenting. So we haven't put this into our model yet, but initial experimenting shows that the heat flux can be reduced by a factor of 50 or more, just from including these non-local effects. I think that, so the alpha-fading waves is, I mentioned here in terms of broadening, but we think alpha-fading waves might also have some role in depositing energy. So we know that MHD waves are going to be produced in a flare. A flare is just mixing the magnetic field around, disturbing it. That's going to produce an MHD wave. The question is, how much energy does that carry? And can that penetrate down into that lower atmosphere? If we have this additional energy transport mechanism, it's going to also increase the lifetime of these events. And so I think we do have some scope to address this. I don't know if they will answer the question, but we do have some lines of investigation.
Sure is worthwhile to pursue that, but again, to envision a physical mechanism that sort of disallows the iron 21 with time not be all over the place, but sort of had this very distinct shape. That is intriguing.
Yeah, I agree.